Hello, I am Dr. Ajay Sharma, Department of Electronics and Communication Engineering, James Engineering Management Technical Campus, Knowledge Park 3rd, Greater Noida. The subject that I teach in this semester is digital communication, and the topic that I discuss today in this video lecture is performance comparison of different digital modulation schemes, then calculation of average probability of error for different modulation schemes, and power, or you must say frequency spectra of digitally modulated signals. So when basically we have three digitally modulation schemes: ASK, FSK and PSK. ASK means amplitude shift keying, FSK means frequency shift keying, and PSK means phase shift keying, right? So these are the three digital modulation techniques. So first we focus on amplitude shift keying. In short, we say ASK. In ASK, there is only change in amplitude of the carrier and frequency phase remains the same, and it required low bandwidth and very susceptible to interference, right? So look at this 10, because in digital modulation technique, we have a message or data signal in the form of a string of 101. So we take a string 101 having 3 bits 10 and 1, and this is the carrier. That should be changed one of the parameter according to 101. So the parameter that this carrier change in this case, because we just talking about ASK, is the amplitude. So whenever 1 come in the picture, then there is a presence of signal, and whenever 0 come in the picture, there is an absence of signals, right? So in that way, this is a case of ASK. Come to the second case, FSK, which is frequency shift keying. In this, amplitude and phase remains the same, but there is a change in frequency. So, and it needs larger bandwidth. That is one of the drawback of that. So whenever one of a data that carrier phase, then this carrier change its frequency high, and whenever 0 come, it change its frequency low. For example, when one come in the picture, this particular have 2 cycles. When 0 come in the picture, this only have 1 cycle. So there is a transition of 2 to 1 whenever there is a transition of 1 to 0. So in this way, there is a change in the frequency. There is a change in the frequency according to 10 bits, right? So this is the case of frequency shift keying, right? So here the frequency is the carrier change its frequency according to 101. And now third case is PSK, which we call as a phase shift keying. In phase shift keying, amplitude and frequency remains the same, but there is a change in the phase of the carrier according to 1 and 0. So, and this is, the bandwidth requirement is less in PSK. So this is superior if you compare ASK with ASK and FSK. So look at this. Whenever one come in the one, there is a transition of 1 to 0. So this point, there is a phase change. So whenever transition of 1 to 0 or 0 to 1, there is always a phase change. Amplitude and frequency remains same. So this is the case of PSK. So here there is some network issue, right? So this is the 3 digital modulation techniques. We already discussed that. Now come to first scheme, ASK, amplitude shift keying, and this is the base. This is the data that you have 1001. This is the data. This is the information signal, right? 1001. This is a digital signal. Now this is the ST. This is the equation that represent binary 1 and binary 0. Whenever there is a binary 1, there is a equation A cos 2 pi FCT, and this is the equation of sinusoidal signal. and whenever 0, then there is no signal. So ST becomes 0. So ST have the equation of sinusoidal signal. So whenever binary 1, then there is a existence of equation a cos 2 pi fc, and this represent a sinusoidal signal. And whenever there is binary 0, there is no equation because of nothing, because signal drop to 0 volt, right? So this is a ASK modulated wave. This is a ASK modulated wave. So whenever 0 means no voltage, whenever 1 come in the picture, then there is a voltage level, right? So 0 is represented by 0, and whenever 1 come in the picture, then this is represented by sinusoidal equation a cos 2 pi fct. And look at the power. Power of any signal actually depends upon the amplitude of the signal. So an amplitude is nothing but it is a voltage. So when you square the amplitude or voltage, you get the power. So a square upon 2 is the power, because a is the amplitude. And power is nothing but it is equal to energy upon time. And time here is TB. It is a bit period. It's a time period of 1 bit. So in this way, a is equals to 2e under root 2b. So you can put this particular a is equals to 2e 2b under root in this place of a. You get this equation. So this is the S1t. S1t is represent 1 and S2t represent 0, right? And this is the final modulated wave of ASK signal, right? Now come to signal space representation for ASK. So clearly there is one basic function of unit energy, pi 1t, which is equals to 2 upon TB under root by TB is the bit period and cos 2 pi fct whenever 0 and TB. T is the time of 1 bit, and S1t is equals to under root T phi 1t, and S2t is equals to 0. So the average energy per bit is E upon 2. So E is equals to 2 EB, right? So binary ASK system is therefore characterized by having a signal space that is one dimensional. So here S1t is equals to under root 2 EB phi 1t, and S2t is equals to 0, and this is the signal space diagram of that, right? S1t is represented by represent certain volume, but S2t is 0 because there is no volume, because the voltage dropped to 0. So there S1t means there is some voltage, and S2t is no voltage, right? And D12 is the distance between S1 and S2, and this is under root 2 EP. So look at this diagram. So this is the boundary. This is the boundary, and this is the boundary that divide the region is region 1 and region 2. When something is region 1, then S1, this is the presence of S1, and presence of S1 means it is represent the equation of ASK signal when represented by 1. And whenever something is region R2, it is S2, and S2 means 0 volt, right? So dependence of the error probability on the distance between two signal points, and in general this is the probability of error. Actually probability of error depends on S by N ratio, right? So D12 is nothing but it represents actually energy. So D12 is the energy, and that represent a noise. So this is signal to noise ratio, right? So probability is always a signal to noise ratio, right? So this is a general. Sorry, there is some connectivity issue. So there is a disconnection with that. So this is a general mathematical model. This is a general mathematical model to represent probability of error of any digital modulation techniques. The only thing that you should know is D12. If you know D12, you know D12 square. Put this D12 in each case, you get the probability of error of that modulation scheme. So in the case of ASK, if you put D12 is equal to this, you get this. So this is the probability of error of ASK modulation technique, right? Now come to concept of constellation diagram. So a constellation diagram helps us to define the amplitude and phase of a signal when we are using two carriers. So actually constellation diagram comes in the picture when you have a certain equation that has in phase component and quadrature phase component, right? So in that way, this is the in phase component on x-axis and quadrature phase means 90 degree. So this is a 90-degree component at y-axis. So this is a quadrature carrier. So this is in phase carrier, this is a quadrature carrier. So sometime in a particular carrier equation is break up into two parts, in phase carrier component and quadrature carrier component. Or in that case, we have to show that particular mathematical model by this constellation diagram, where this is the resultant amplitude and this is the phase angle between the two components, in phase and quadrature phase. Okay. Then constellation diagram of ASK. Look at this. ST represent this much, and this is the equation of sinusoidal signal, and that represent binary 1. ST is equal to 0. When binary is 0, there is no signal, voltage drop to 0. So look at the quadrature. This is constellation diagram. Look at that. 0 and 1 are on the same phase. 0 is there, 1 is there. So whenever 1 is represented and whenever 0 is represented, they are in the same phase. So in phase component are there, right? But 1 is represented by gas A cos omega ct and 0 is represented by this 0. Use of ASK, or you can see this frequency spectrum also. With the help of frequency spectrum, you can calculate the bandwidth of any modulation scheme. So by seeing the frequency spectrum, if you need to calculate the bandwidth of a certain modulation scheme, so you should draw its frequency spectrum. Frequency spectrum just give you the idea which frequency component is minimum and which is maximum, and maximum minus minimum frequency component is called bandwidth. So for that you should draw a frequency spectrum of any modulation scheme. So in this way, use of ASK, the simplest and most common form of ASK operated as a switch. So the use of ASK as a switch, on-off keying. Sometimes ASK is also called on-off keying and very high speed over optical fiber. So this is frequency spectrum ASK. This is the power and this is the frequency. So these are the frequency component and these are the power. This is the signal power, right? These are the frequency component, this is the power. So here we can choose our FC so that the modulated signal occupied available bandwidth. So in that, by seeing the frequency spectrum, you can calculate the bandwidth of any modulation scheme. And frequency spectrum is nothing but it's a graph. It's a characteristic between frequency and signal power. Then come to frequency shift keying. In frequency shift keying, the sinusoidal signals change its frequency by keeping amplitude and phase constant with respect to 0 and 1. So if you look at that, this is a carrier, this is a modulated signal, this is a FSK modulated signal. In FSK modulated signal, only frequency is to be changed according to 0, 1, 1, 0. So whenever 0 come in the picture, the frequency of this carrier is minimum, and whenever 1 come in the picture, it is maximum, right? So the frequency of the carrier is changed from minimum to maximum, maximum to minimum, depending upon 0 to 1 or 1 to 0. So here the frequency change. So S1T has this equation, S22 has this equation. The interesting thing is that the amplitude remains the same. So the energy or the power associated with each equation remains the same, because power and energy depend upon the amplitude. So amplitude remains the same, means volt remains the same, means energy, power remains the same with the two conditions, 1 and 0. So this is the change only in frequency. So here the frequency F1 to represent 1, here the frequency F2 to represent a 0. And transmitted in a signal energy per bit remains the same, and this is the energy of S1T of 1 bit period. 0 to TB is the time period of bit. Whether it is 0 or it is 1, it is always equal, right? So F1 is the transmitted frequency with respect with separation delta F. Delta F is the separation between F1 and F2. So this delta F is F1 minus F2. And delta F is selected so that the S12 and S2T, S1T and S2T are orthogonal. This is the condition. 0 to 2B S1T into S2T dt is equal to 0. This is the condition of orthogonal. Now signal space of for FSK. Unlike ASK, here two orthogonal basic functions are required to separate S12 and S2t. So this is represent phi 1t, this is phi 2t, this is the required equation. Here is F1, this is represent F2, and this is the bit period 0 to 2b. So signal space representation is S1t is this much, S2t is this much. And this is the decision region of ASK. So if you see this constellation diagram, this is in phase component, and this is out quadrature phase component. So S1 message point is there, S2 message point there, and here is a line. Here is a threshold. If something is below, if something is in this particular region, then we declare S1, and S1 represent 1. When something is to be there in this R2 region, then we declare S2, and S2 represents 0. Isn't it? So the receiver decides in favor of S1t if the received signal point represented by the observation vector R, which is fall inside the region R1. This occurs when R1 is greater than R2. So when R1 is less than R2, R fall inside region R2, and the receiver decide in favor of S2t. So in that way, on the basis of S1t and S2t, the receiver declare whether 1 was received or 0. And this is the probability of error of Fsk. So it is again have the same general formula. It only depends on D12, right? Here the D12 is coming out to be under root 2 EP, isn't it? It is a distance between the two message points. So put this D12 is here, you get this probability of error. Or in general, probability of error always equal to the under root of S by N ratio. So this is EP represents signal power, and N naught represent noise power or noise energy. So this is the probability of error of Fsk. Now binary phase shift keying. In binary phase shift keying, what's happened? The carrier phase is changed by keeping amplitude and frequency remains the same. So look at this. Whenever 0 to 1, 1 to 0, there is always a phase shift. Look at this, 0 to 1, here is the phase shift. 1 1, no phase shift. 1 0, there is a phase shift. 0 1, phase shift. 1 0, again there is a phase shift. 0 0, no phase shift. 0 1, again phase shift. So there is a phase shift according to 0 and 1, right? And this is the equation that represent 1. S1t is the equation that represent 1. Here again energy, here again amplitude remains the same if you take the two cases. So because amplitude remains the same. So when amplitude remains the same, again energy of the signal that come under 0 or come under 1 are equal, because amplitude remains the same. So energy power depends upon amplitude depends upon voltage, right? So when you represent 0 is only change in pi. So there is a pi change, right? So because phase change from 0 to 180 degrees, so there is a shift of pi. Pi represent 180 degree, and this is the case. And by trigonometric formula, this become that, and minus come in that. And t time period is 0 to b, where tb is the bit duration. So transmitted signal per bit is this much. This we are already familiar with this Parseval theorem. According to Parseval theorem, this is the two equation. This is the energy, and both the energies are equal because the amplitudes are equal, and it is EB, right? So the pair of signal differ only in relative phase shift of 180 degree. Signal space representation of BPSK. Clearly, there is no basic function of unit energy. There is one basic. Clearly, there is one basic function of unit energy. We have phi 1 and we have S1t, we have S2t, and this is the scenario, right? This is 180 degree shift. S1 is here, S2 is here. Only difference is 180. You know, this is 180. This is 90 and this is 180. So D12 here comes to be 2 under root EB. So by knowing this D12, distance between the two message points S1 to S2, S1 and S2. Now the probability of error depends upon D12. This is the case. First of all, okay, decide we focus on the constellation diagram. Then the optimum decision boundary is the midpoint of the line joining these two messages. Of course, this is the midpoint. This is the midpoint between the 2 points. So something is to become an R1 region, then declare as S1. S1 means 1 bit. When something in region R2 that have the message S2, then the receiver declares 0 because S2 S2 represents 0 and S1 represents 1. So this is the decision rule. So signal S1T or binary 1 was transmitted if the received signal point R fall in the region R1, like in this region. Otherwise, signal S2T for ordinary 0 was transmitted, otherwise R is less than or equal to 0. When R is less than or equal to 0 means region R2. Region R2 means S2. S2 means 0. Region R1 means S1. S1 means 1. And this is the boundary. Decision boundary. Then probability of error. Again, probability of our general formula is this much: D12 square 2 n naught. Here D12 is 2 under root EB. So put 2 under root EB here, and you can get. Then you can get the. Since signal S1T and S2T are equally likely to be transmitted, the average probability of error. So this is actually VA calculate average probability of error, and this is nothing but 2 EB n naught. Again, have the same type of formulas. Again, I said that probability of error depends upon S by n ratio. So EB upon n naught is always a S by n ratio representation, and P is the probability of error. Then this particular diagram, Constellation Diagram, advantage of PSK. So if this is 1, this is 0. Look at the difference between 1 and 0, 180 degrees. So 1 by A cos omega ct, 0 is again A cos omega ct, but a negative. This negative shows if A cos omega ct waveform start from this side, then minus A cos omega ct waveform start from this point. And this point and this point, the phase difference is 180. This is the case. This is a very, very good diagram to understand the concept behind this PSK. So in PSK, noise can be changed. The amplitude is here, but it can change the phase. Then it can change the phase. Means noise can change the amplitude is here, but it's very difficult to change the phase. Means the noise effect are minimum in PSK. In other words, PSK is less susceptible to noise than ASK. So PSK is superior to FSK, ASK because we do not need two carrier signals. So this is again a summarization of these three modulation schemes. So here the case of BPSK, BFSK, and BASK. B means binary. This is binary PSK. This is binary FSK. This is binary ASK. These are the D12, and on the basis of D12, we have probability of error different scheme. This is right. So you should remember what is D12. Then this is the by putting D12 in general formula of probability of error, you get the specific probability of error mathematical model, right? So these expressions illustrate the dependence of the error probability on the distance between the two signal points, and this is the very much advantage because probability of error depends upon the distance between the two signal points. So in general, this is the equation of probability of error. And thank you very much.